Hi, I'm Neve. I'm president of StrathSEDS, and today I will be introducing you to our entry to the Mach 22 launch competition, which we have named RF Magic. So the reason we've named our project RF Magic is because it is a very radio-centered mission. So obviously our primary mission, as defined in the competition guidelines, is to use standard sensors to measure altitude, longitude, and latitude of both our rocket and our payload, which is a CANSAT. But our secondary mission is going to be to use 2 ground stations, a rocket, and 2 CANSATs to create an aerial mesh network, which our electrical team will go a bit more in depth on later. And we also have a tertiary mission, which is to use strain gauges, accelerometers, and other sensors to gain information to help us develop our entry for next year, which we hope will be Stratosphere 2. So for our flight plan, this first stage is that our rocket is launched. After this, our primary and tertiary mission data starts to be gathered as our rocket ascends, hopefully to bang on 1 kilometer in altitude. Once it reaches apogee, both CANSATs are ejected and all parachutes are deployed. And then at stage 4, our mesh network is initialized and the altitude and GPS are still being measured. Strain gauge data can still be looked at for reusability, so we still want to have that data recorded. And then stage 5, a message is sent from ground station to ground station and a reply is sent back. And we're going to try and do this through our aerial mesh network. And this is to simulate, for example, if you have a building in between your 2 ground stations and you have your CANSAT descending above them, you can send a message via that CANSAT, almost like a communication satellite. And then stage 6, everything hits the ground and everything that we have launched will have a buzzer. We learned our lesson last year. We don't want to spend an hour looking for all of our nodes. So all of the buzzers will activate and hopefully GPS data is still being transmitted, which will help us recover. And then stage 7, everything is recovered. We analyze our data and we make our post-flight presentation. We're hoping to already have a template for our post-flight presentation before launch so that on the day we can just plug in our pretty graphs and everything. I also want to introduce you to our team. We have quite a big team this year using the full 15. At the moment, we're struggling to get an academic advisor. We're waiting to hear back from a couple of members of the aeromechanical department, but we'll update you on that as soon as we can. So our leadership team is myself. I've been the team lead for semester 2 with Pablo Alvarez, who's the semester 1 team lead before he went to Valencia on exchange. We have a sizable mechanical team, as you can see here, as well as a 3-person electrical team and a 2-person coding team, who have all been very hard at work and making sure we will be ready for launch day. I'd now like to pass you over to Matthew, who will be taking you through our launch vehicle concept and some SolidWorks models that he's drawn up.
So this is the current assembled CAD of our rocket, Stratosphere 1. We adapted this design from the open rocket model, which is shown in our next slide, and there are a few notable features in our CAD model. You might notice the 2 CANSATs. This will offer another node to the electrical team's aerial mesh network, though it will also mean double the building for us. Another notable feature is the aluminium ejection block, which can be seen above the motor mount. This should serve to uniformly push out the payload from the body tube and eject a nose cone as well. Now, this is a closer view of the motor and fin mounting. Centering rings and adhesives are planned on being used to hold the motor mount tube in place, as well as this our 3D printed fin concept is going to be integrated between the centering rings and held in place also using lots of adhesives. Now, the motor mounting tube should not require an engine block as the motor we have chosen should have a stop on the end, so that's been omitted from this design. Now, moving on to our simulation models. We used OpenRocket to get numbers for our rocket design. Shown at the top is our max payload rocket design, which is predicted to just make the 1 kilometer apogee mark. As well as this below, you can see the same rocket, though this time with no payload. The CANSATs are still visible here, but their mass has been set to 0. The rocket is thankfully stable in both scenarios, so it can be launched without a payload in it and successfully fly. We also used OpenRocket to select our motor. We chose to use a Cicerone i287SS rocket motor. Now, this is a 4-grain rollable motor, meaning that it should be fairly easy to use after the competition, as well as providing enough performance to take the rocket to the required apogee for this competition while also staying within the class and impulse limit. Now, one assumption that has been made in OpenRocket is that it's going to be launched directly upwards and also with very minimal wind or turbulence. Now, in reality, this isn't the case, so real-life performance will vary a little bit from the simulations. Speaking of the simulations, these are the numbers in detail that OpenRocket produced for max and minimum payload. OpenRocket sometimes suggests if there's any problems or issues with the numbers that it finds during flight. However, both sets of these numbers didn't yield any warnings, thankfully. OpenRocket also produces graphs of the flight. There are some shown here. This is a fairly nominal flight graph that we've been given, and thankfully there are no scary big red flashy numbers that we need to worry about. Now I'm going to touch on payload integration a little bit for you. Our payload, as I mentioned, includes 2 CANSATs and a nose cone. Inside this nose cone is where we're mounting our avionics bay. So the CANSATs should easily slip into the body tube as we're planning for a little wiggle room between them. The nose cone will also slide into the tube at the top, however, is planned to be flush or just a bit tight with the rocket tube so that it stays in during flight. To remove all of this at the apogee of the flight, the ejection charge is going to cause the aluminium block to force the payload out the front as well as the nose cone off the front at the same time. I should note here that there are no obvious parachutes shown on the CANSATs here, but they will have parachutes in reality. Now, last thing I'm going to touch on here is the manufacturing process and material selection. So the plan for our nose cone is to 3D print it using PLA. 3D printing is quite cost effective for us, and it also lets us easily print another one ahead of time or spares, or easily modify it if we need to make changes. 3D printing from a CAD model also lends us quite a high degree of precision and customizability to design. And the final factor, especially for PLA+, is that it's a sugar-based filament through chemical processes and stuff, and is slightly less bad for the environment than other plastic alternatives. So our main body and our motor mounting tube will each be made of the same material, that is blue tube, which is a material listed on the Apogee Components website. This material has a higher performance than normal phenolic or cardboard tubes, and also means there's less manufacturing for us if we buy like standard sizes that we don't have to modify an awful lot. One modification we will have to make is small holes to put the fins through though. For those fins, the plan is either to use reinforced plywood or once again 3D print them as shown in the CAD model earlier. Using plywood would be lighter than the 3D printed filament and also less brittle, though it offers a little bit less design flexibility. Finally, we have the material choices for our CANSAT body. The plan is to 3D print the CANSAT body and to cap the ends with laser cut acrylic, much like last year's CANSAT shell. This shouldn't interfere with electronics, unlike some of the metals which we had previously considered to use for the CANSAT body, though it won't be quite as strong as the metals. Anyway, thank you. I'm going to hand you off now.
So, as for the overall electrical architecture for both the rocket and the payload, this is how it's planned right now. The system will be universal between both the rocket and the payload, meaning we can manufacture the same design of our main board and then specialize each board for the rocket or the payload, depending on their needs. The board will be based on an STM32 microprocessor. The specific one will be chosen later, as we will have to fight with chip shortages. That's the same for all other components, but the architecture right now is to have as many components as we can concentrated into this one board, only interfacing with a second GPS board that will allow us to position it more efficiently inside either the payload or the rocket. The batteries will most likely be standard lithium-ion batteries, but that's also subject to change. And the main board will have 3 ways of interfacing with the outside world, mainly using the USB/ST-Link for debugging and programming, the GPIO pins for external sensors, like the strain sensors for the rocket, and an SD card reader for recovery data retrieval. We have current short-term plans on manufacturing version 1 of our main board using offshore GLC PCB manufacturing services. We hope to use their services of assembly as well for our first designs. But as we go forward and the design matures, we hope to get in contact with local manufacturing firms or GLC PCB as well to have the manufacture and assembly of the main board sponsored as much as possible. But everything that we won't be able to have done by external companies, we will finish in university laboratories that we have access to. Now I'm going to pass it off to Andrew, that's going to go over the sensing systems that the main board will have.
Thank you, Jakub. As he mentioned, we are using universal boards for the CANSAT and rocket. These boards will contain varying sensors. The rocket will contain an IMU, which has an accelerometer, gyroscopes, and a magnetometer. There will be pressure sensors in both the CANSAT and rocket, which will act for altitude and temperature. The GPS module will be in the rocket and CANSAT for tracking of it, and there will be strain sensors in the XYZ axis in the rocket alone. The strain sensors are for future data gathering for future endeavors. I will now pass over to the coding team who will explain how the data is transferred.
To record telemetry and view the CANSAT's onboard flight systems, we've decided to create a web page that displays data received from the ground station antenna. For the ground station to receive data, the CANSAT will send chunks of in-flight data to an Arduino on the ground via antennas. Any data that is mission critical, altitude, air pressure, or GPS data, will be stored in the CANSAT's dedicated SD card and then sent to the ground station simultaneously to ensure the data can be recovered intact. On screen, you can see an early prototype of the ground station UI, showing the CANSAT status at the top, live data in the green blocks, and a map in the middle to show the GPS location. We're planning on showing live visualizations of data with graphs and maps during the flight on the webpage.
As for technologies, we're using Node.js for the server. The server processes the data from the ground station and generates the web dashboard. For the microcontrollers, we're planning on using Rust. For the microcontrollers, we're planning on using Rust. We've begun programming the ground station and the server. However, we've not yet started working on the CANSAT and rocket as they don't exist yet.
So this will be the design concept for the CANSAT, given the current dimensions we have right now. For the diameter, we will have 68 millimeters, and for the length, we will have 115 millimeters. Basically, this CANSAT model has batteries in PCB holder, the batteries that are in red, the PCB that is in green, and where we have the shell, we will have the two caps and the rods. Basically, the rods will help the batteries and PCB holder to keep it in place and to keep it steady during the launch and during the mission. And the holder will be made using a 3D printer, and the way it was made is just in order to take advantage of the space we had available, and we are pretty sure that it will work and perform perfectly during the operation of the mission.
Each of our descending vehicles has an individually sized parachute so as to allow it to descend at the desired descent rate. This is slightly spread out so that our radio nodes can be spread out in space as they descend. The CD values used for this were extracted from a CFD analysis done by a Korean university, and you can see on the screen our target descents and parachute diameters. Safety is key with any project like this, and of this table of risks that we've created, there are a couple key ones that I want to point out here. Firstly, being that there's a COVID outbreak within our team. Firstly, we'll take every step we can to avoid this happening in the first place by social distancing, wearing masks, etc. But should, unfortunately, someone become infected in our team, we'll have other members ready to take over any work that they were doing and isolating those team members that are affected and potentially conducting our meetings over Zoom, should it be needed. And secondly, range safety on the day. This has to be mitigated by doing stringent tests in the lead up of critical systems of the rocket and by following all advice from range safety officers to keep everyone safe. This year, our budget is just under £3,000. This budget includes money for spares and tools which we'll be using. And we have a more detailed list in a spreadsheet that's not shown here. As for getting that money, we have three main funding sources at the moment. The university's Mechanical and Aerospace Engineering Department provide the majority of our funding, as well as two other engineering organizations whose grants we'll be applying to. Our electrical team is also looking for corporate support for their PCB manufacturing, and finding more sponsorship is on the table for us. Thanks. I'll pass you on to Neve, who has some closing thoughts.
So this is what our project management timeline is looking like at the moment. So the mechanical team made a Gantt chart for where we want to be by PDR, CDR, FRR. And then at the bottom, you can see we've added the electrical internal deadlines that they've set for themselves. So these aren't like long planning segments like they are with the mechanical team, but we wanted to include their internal deadlines in this as well. So to conclude, for the mechanical side of things, what we've done so far is mostly working on preliminary SolidWorks and open rocket models to make sure that everything that we've designed on paper works well in our simulations as well. We've also started work on our manufacturing testing plans. Moving forward for CDR, we want to finish our manufacturing testing plans and then start manufacturing all of our structural components. And as we test, we want to test those as we manufacture them so that if we need to go back and redo something, we still have the time to. Two things that we might have trouble with going forward is finding lab space. It's something we've struggled with the university, but we're working on that and we think we've secured something now. And secondly, securing funding is something that we've been finding quite difficult, but we've managed to get ahead of that so far and we think we should be okay. Finally, also, finding an academic advisor is something we hope to have confirmed by the end of the week. We're just working out a few last details with members of our academic department. I'll pass you over to Andrew, who's going to go through the electrical conclusions for the PDR.
Okay, so for the PDR, so far we've designed the version 0 of the sensors, power unit delivery, microprocessor unit, and radio boards. For the next steps, we are to develop and refine our CANSAT and rocket PCB design, begin manufacturing and testing of SED version 1 of the CANSAT and rocket PCB. Potential challenges at this stage would be calibration issues, component selections due to potential the current chip shortages, and general market volatility, and general electrical issues. To address these, we understand that we may need to change components on the fly as market changes. There may be components which are incorrectly sized for the areas we need to put them in. So they will either have to use items with greater size differences or alternatives. And yeah, that's about it.
So thank you, Andrew. And on that note, we'd like to thank you for listening to our PDR presentation. If you have any questions at all on anything we've talked about, feel free to get in touch with us and we'll try to answer them as best we can. And we look forward to moving on to CDR.